here's an understatement. Electrons as dots is a drastic oversimplification. We just got done talking about all these crazy wave functions and these levels and all this different stuff, and now we're just drawing dots? It is a drastic oversimplification, but it's a heck of a lot easier to think about. One thing we do need to think about, though, is those electrons are not always shared equally. Did you ever have to share a bed with a sibling, maybe at grandma's house or on vacation or something? How'd that go? Not well, huh? There's always one person that either takes up most of the bed or pulls the covers over, and the other person is left on the edge and cold, right? Because you're sharing a bed, but you're not sharing it equally. Well, that's what happens with electrons as well. So if we look at, this is hydrogen over here and fluorine. And, we can draw the Lewis structure for that. We got a pair of electrons shared here, but that pair of electrons is not shared equally. The fluorine is hogging the blankets. It's hogging the electrons. It's pulling them over. And so these electrons are spending more time around fluorine than they are around hydrogen. So this is an analogy that I forgot to do yesterday with my class. So electrons, kind of squirrely, unpredictable little creatures. They remind me of my sons when they were young, little boys. Who knows what they're going to do next? They're awesome, but very unpredictable. So I see these electrons as little boys, and hydrogen is one house, and fluorine is the neighbor's house. And these two little boys in this bond are playing. They can play at either house. Well, at hydrogen's house, they have black and white television and an old VHS player with some, do you even know what that is? With some Thomas the Tank Engine videos. And if you're hungry, you can have tap water and some Ritz crackers. Over here at Florian's house, they have a swimming pool in the backyard. They've got big screen TV. They have all the game systems. They have a soda fountain in the kitchen. I want one of those. And Mom will order you pizza if you're hungry. Where are those two little boys going to spend more time? At Florian's house. Because it's more attractive to them, right? We're going to talk about electronegativity, which is how attractive is a given atom for the electrons in a shared bond. So these electrons are not shared equally, and because those have charges and they're not shared equally, the one end of this molecule becomes a little bit negative. Whoops, wrong marker. A little bit negative, and the other side is a little bit positive. This letter is a lowercase Greek delta, which looks a little bit like a regular D that's slumping as a posture problem. So this means partial positive and partial negative charge. So this is called a polar covalent bond. It's covalent because the valence electrons are being shared, but it's polar because we have different ends, like the North Pole and the South Pole are different magnetically from each other. Here, the ends of the molecule are different electrically from each other. So if we just had these, this would be a gas at room temperature. These molecules are just floating around in space. If we apply an electric field across these two plates so that this plate is negatively charged and that's positively charged, all of these little molecules are going to swing around almost like a compass, right? And they're going to point their positive ends toward the negative plate and their negative ends towards the positive plate. Those are polar covalent bonds, unequal sharing. So we can think of them as being between ionic bonds and pure covalent bonds where the sharing is equal. Ionic bond is the transfer of electrons, covalent is sharing, polar covalent is sharing but not equally. Any questions? So electronegativity can be defined as the ability of an atom to attract electrons to itself in a chemical bond. So in the analogy, it's, each of these atoms is a house, and the more electronegative one has more features of that house that are attractive to little boys. Trampoline in the back, fun stuff. And so up here, fluorine is the most electronegative, and so it's given a value of 4. And then everything is downhill from there. So this property of electronegativity is inversely related to atomic size. So we learned that as you go across the period, atoms get smaller. As you go across the period, electronegativity gets larger. As you go down a group, atoms get larger. As you go down a group, electronegativity gets smaller. So it's opposite. But I usually just think of fluorine is king of the hill, and you can compare two elements and see, well, who's closer to fluorine? That one's going to be more electronegative. Notice that the noble gases don't show up over here because they form almost no bonds. So we just leave them out of this because there's only a few compounds that they make. So we leave them out. There might be a homework problem or two where you might actually need to use these electronegativity values. There won't be anything like that on a test. This is something we should be able to do, though. Arrange these elements in order of decreasing electronegativity. First, we have to find them on the periodic table, because the periodic table is the key to figuring these guys out. So we've got phosphorus and sodium and nitrogen and our good friend Al, aluminum. This wants us to show it in order of decreasing electronegativity. So that's larger to smaller. The test bank has a lot of questions like this, and sometimes students misunderstand the question, and so I really want you to be able to understand the question. So we're going to start with the most electronegative and go to the least electronegative. And the way these choices have been set up, they have greater than signs, which is also helpful. So let's just have a quick lesson in greater than, less than, because I know that's confusing for a lot of people, because they're just flipped of each other, right? So this is a greater than sign, and that's a less than sign, and I don't care if you know that's what they're called. But if you see something like this, you should recognize that whatever we're talking about, this one's bigger than that one. You see, this end of this sign is really small and pointy. That's on the small side. And this big side over here, like it's opening its jaws to eat something, that's where the bigger one is. So this is saying that this one is bigger than that. It's more electronegative. Okay. So we don't need to use electronegativity values. We don't even need to really think about atomic size or anything like that. Just think about, well, who's closest to fluorine? Which of these elements is closest to fluorine on the periodic table? Nitrogen. So that tells me that nitrogen is going to be the most electronegative. Which one is furthest away? Sodium. Way over here. So sodium's going to be last. And then we've got Al and phosphorus. Phosphorus is closer to fluorine, so phosphorus is more electronegative than aluminum. If you have a question like this, don't look at the choices. Set up the arrangement using your own good brain, and then pick the one that matches. Because when you look at these and start to think about that gets ugly fast. So the correct choice then is A. Any questions? In general chemistry, you almost never need to know the exact electronegativity difference. You just need to know if the electronegativities are different. And if so, which one is more electronegative? And so being able to put these in order is a good skill. Well, the degree of bond polarity depends on how different the electronegativities are. So at one end we have pure covalent, these electrons are shared perfectly equally. So this would be like two houses where they've got exactly the same stuff. You know, live in a subdivision, it's like cookie cutter houses. The houses are like exactly the same, so who can even tell the difference? So those guys are just going to bob back and forth. And then over here, this is taking the analogy a little too far. This is where the one little boy is so attracted to this other one that he actually moves over there, and he doesn't live here anymore. So he's transferred. He's moved to the other house because it was so much better than his house. And here, the electrons still spend some time at both houses, but they're going to spend more time at the one that's more electronegative. It's more attractive. Yeah.
How would we notate that it's charged?
How do you notate that?
Or do you?
Yes, you do. So, one way is to use these little deltas. So that's partially negative and partially positive. And the other thing you can do, like if we're doing, like if we have this molecule or this bond and we want to indicate the polarity of the bond, we can use an arrow. And the arrow is going to point to the more electronegative one. And so I think of this as, you know, dad's coming home and big brother's out in the yard and he's like, where are the kids? And he points, they're over at that house, right? So fluorine's more electronegative, so the arrow points to fluorine, and then I guess to make it look different than a regular arrow, we're going to make this side a plus. So this is the positive end of that dipole of the polar covalent bond, and this is the negative end. That's where the electrons are. Somebody's pointing. They went that way. Okay? So the polar covalent bonds are kind of in the middle here. Kind of have to draw some lines, even though they are a bit arbitrary. So we say that we have a pure or nonpolar, I prefer the word nonpolar covalent bond if the difference in electronegativity between the two elements is 0.4 or less. If the difference is 2 or greater, that's going to be an ionic bond. If it's somewhere in between, it's a polar covalent bond. Now, I just finished saying that we don't need to memorize all those electronegativity values, and we're really not even going to use them. We do need to be able to identify, is this a polar bond or a nonpolar bond? So this is my shorthand or cheat way of doing this. What kind of bond do we have? Well, if we have a metal and a nonmetal, that's going to be ionic. We learned that in chapter 3. That's ionic bonds, because the metal will lose electrons and the nonmetal will gain electrons. What if we have identical nonmetals, like 2 carbons? What's the electronegativity difference between carbon and carbon? 0, right? So nonpolar, two nonmetals that are the same, carbon, carbon, hydrogen, hydrogen, whatever you want. This is going to be a nonpolar covalent bond. What if we have 2 different nonmetals? This is not 100%, is not true 100% of the time, but it's true enough to get us where we need to go. If you have 2 different nonmetals, I expect you to predict that it's a polar bond. Polar bond. The one exception that I want you to remember, there's a bunch of them, but there's only one that's important. If you have carbon and hydrogen, a carbon-hydrogen bond, the electronegativity difference is 0.4. It's right on the edge, but it's a nonpolar bond. Carbon-hydrogen bonds are all over the place in OCHEM, and we need to remember that those are nonpolar. But anything else, I expect you to tell me it's polar. It's not always true. We go back and look at this. So here, carbon and sulfur, they actually have the same electronegativity values. So that would be a nonpolar bond, but I'm not going to ask you about one like that. I would still expect you to predict that carbon-sulfur is polar. Did you have a question?
Yeah, is the value of the electronegativity, is that given on the periodic table, or is that
No.
something that we have to memorize?
You would have to memorize if you wanted to use it, and it's not worth the space in your brain. Yeah. I have a periodic table in my office, and it has a whole bunch of different stuff on it, because you can get up close to it, right? And it's big. So that has electronegativity values on it. But a standard periodic table doesn't. There's just not room. Any other questions? So a dipole moment is another way of measuring the bond polarity. And so this has to do with that separation of charge. Dipole moment happens anytime there's a separation of positive and negative charge. It's dependent on the charge magnitude and the distance between the charges. We're not actually going to calculate any dipole moments, but you need to know that it can be calculated. And there is a unit for that. It's called a debye. We're not going to use that either, but now you've heard about it, right? So we will talk about dipole moments, but we're not going to talk about calculating them or anything. A dipole moment is when you have a separation of charge. So you go one end is a little negative, one end is a little positive. This is just a summary of the different types of bonds. And if we look at these guys here, Cl2, two chlorines, nonpolar. Here, HCl, two different nonmetals, nonpolar. Sodium chloride, metal and nonmetal, ionic. So don't worry about trying to remember those numbers. Another way you could measure the polarity is called percent ionic character, and we're not really going to do much with this either. We're just going to look at it on this slide. That would be the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was actually completely transferred. So here is the small print. No bond is actually 100% ionic. So we're talking about transferring electrons from a nonmetal to metal. It actually doesn't ever happen all the way. So we need to be okay with that, and then we can kind of ignore it. Okay. So here we're looking at percent ionic character as a function of the electronegativity difference between those two elements. And they consider anything over 50% ionic character to be an ionic bond. So here's 50% right here. So there's this cluster up here. And what kind of elements are these? Metals and nonmetals, right? These guys are ionic. And then there's this guy. He's trying to be in that group. Two nonmetals, but fluorine is the most electronegative, and hydrogen is like the least of the nonmetals. And so this is the most polar bond that two nonmetals can make, but it's not quite ionic. And then over here, with much lower percent ionic characters, we have different nonmetals together. So those are polar, but not as much. So this is the kind of question we should be able to answer. Determine whether the bond formed between each pair of atoms is nonpolar covalent, polar covalent, or ionic. And so these are the little rules that I scribbled up in the corner. I should probably make that into a nice slide one day. Iodine and iodine. What kind of bond is that going to make? That'll be a nonpolar covalent bond. They're going to share those electrons equally because they are exactly the same. How about cesium and bromine? Ionic. I love how everybody's eyes went to the periodic table because that's where the answer is. Where's cesium? Oh, it's way over there with the metals. Metal, non-metal, this is an ionic bond. Phosphorus and oxygen. Covalent, polar or nonpolar? Polar. So in a question like this, I would only ask you ones that are actually polar. So if they're different nonmetals, assume that they're polar. Any questions? So the percent ionic character and the debis and stuff and the little differences, it really just all comes down to, can you do this?